Okay, good morning, everyone. Well, only Elga here and me. So we are going to study the use of a specific class, yeah, Scikit-learn. So actually, last week after the presentation on your quiz, take-home quiz, we have uh, introduced a little bit about Scikit-learn. Scikit-learn is a specific class, yeah, in or object within the that is made for Python. Yeah, it is made to be used in Python to implement certain algorithm in machine learning. So in machine learning using Scikit, many tasks that we had to what do you call it, make ourselves, yeah, in previous chapters, perceptrons and then other line, and we have to define everything by ourselves, and we have to define using the standard algorithm by Python, and then develop the code ourselves. So when we need to do much more of application oriented implementation, so we don't really want to know the process, yeah, behind the black box, especially when as we are biomedical engineer and we are more towards how to apply the machine learning in real healthcare problem, for example. So what we can use is a class like this Scikit-learn, a standardized class like this Scikit-learn. So if you go to Google, Scikit-learn, you will find the resources about Scikit-learn in the scikit-learn.org. So it contains all the documentation related to the classes, the methods, the method to object used within the Scikit-learn class. So you could use this. Yeah, you could use this, and if you want to learn on the detail, you can learn from this website. Actually, there are other classes, yeah, available for us to use, which is Tensor. I'm not sure if we have time to study the class. If not by me, maybe you can ask Paulia, but I have asked Paulia maybe later in the second half of this semester to teach you all more specific about the application in healthcare, yeah, the advanced application in the healthcare. So I'm teaching the basic. Regardless, then you need to do your own study, because with 2 hours per week, it is not that enough to study the whole aspect of machine learning. So you could read from the internet, yeah, many available resources. Okay, so we will use this scikit-learn to implement some of the popular algorithm. Besides what we have learned, Perceptron and then other line, we will also learn about new algorithm that popular for classification, including like logistic regression, support vector machines, SVM, and decision trees. So scikit-learn machine learning library is a user-friendly Python API. So for example, when in the previous chapter, we need to define every variable by ourselves, and every function we need to make ourselves code, write the coding ourselves. In this case, that we do not, when using scikit-learn, we do not need to have such hassle. Yeah, so we can immediately use the function, the sum of the standardized function used in machine learning. So the strength and weaknesses of classifier with linear and non-linear decision boundary will also be studied in this chapter. But actually, in the quiz, you have tried, especially in the bonus question, I have asked you to try using non-linear boundary condition, for example, using quadratic or cubic activation function to try to separate the boundary between the classes. And apparently, for example, in the case of Elga, you have succeeded to classify the two classes quite successfully. So when choosing a classification algorithm, you need to select the features and then collect the training sample. Choose a performance matrix. For example, the accuracy you can choose as a performance matrix. And the accuracy is how much percentage that your prediction based on your machine learning algorithm can be close to the actual class given using the supervised learning algorithm. After that, you choose algorithm classifier and optimization algorithm. What kind of classifier algorithm and optimization algorithm that you choose. Sometimes different algorithm will behave differently according to the data. Then evaluate the performance of the model and finally tune the algorithm. Okay, let's go back again to the iris data. Yeah, and the first and simplest example is to try using Perceptron as the basis of the machine learning. Yeah, this is the one of the earliest algorithm in neural network as well, that is used to try to recognize pattern. So we have again the iris data containing three different classes, yeah, setosa, iris versicolor, and iris virginica. And then there are four features that are used to separate between these different classes: sepal length, sepal width, petal length, and petal width. So the sepal length is in the iris data is in the zeroth column. Yeah, the first column is in Python always labeled as 0. Sepal width is in the first column. Petal length is in the second column. Petal width in the third column. And the fourth column is the class level. And there are 150 sets of data with 50 data set for each of the iris species class. Okay, so this sepal length, sepal width, petal length, and petal width becomes the features that we can use to classify these three species. That there are attributes, measurements, or dimensions. Okay, so first is assigning the petal length and width of the 150 flower samples to the feature matrix X and corresponding class label of the flower species. Yeah, the class label means in the last column to the vector Y. Okay, so I would like to ask you to also open the chapter 3.ipynb that I have shared in the Google Classroom, yeah, and open it using Google Colab. Okay, it's in Google Colab, and let's run it cell by cell. In the first cell, for example, it asks to uh, load the watermark. Yeah, this load watermark. However, usually this is the code is come from the book by Mr. Sebastian Raschka, yeah, entitled Python Machine Learning. Python Machine Learning. But if you using the standard Google Colab, usually it will not cannot be run smoothly. What you need to do is you need to install the module watermark itself. Yeah, so you example here using this command pip install watermark, so that then it will be installed in your Google Colab. Yeah. So the pip install is a command that we will use when we want to use specific module developed by certain people. Yeah, to it contains class methods, etc. Okay, so afterwards, then here this one we want to import the Scikit-learn. Yeah, so we want to import the Scikit-learn. This is the version. Yeah, you need actually to run this. So if it is there, usually Scikit-learn is quite a standard. So usually Google Colab already has it installed. Okay. So from here, if this is to import the image, I'm not sure if this can run. Oh yeah, it's creating a problem. It just doesn't have any output. So first here, yeah, this is what is the slide mentioned that we want to import first the 150 flower samples to the feature matrix X and the corresponding class labels of the flower on the last column to the of the flower species to the vector Y. So first is we import from the Scikit-learn import dataset. Okay, so this is what is nice with Scikit-learn. You don't need to download the specific data from its specific website anymore, right? Like in the previous one, we have to download it from the specific GitHub or specific site that contains this iris dataset. The sklearn module already contains that as its standard dataset. So when we then import numpy as np, so this is the standard numerical numerical module for Python. Then iris equal to datasets. This is dataset contains the whole dictionary or structure of the that the sklearn has. Dot load underscore iris. So this will load specifically the iris data into the variable iris. Then x, in the x variable, we will put, we will load the iris data, all the rows of the data sample, especially, but we are only concerned now to use the second and the third data, which is the petal length and petal width. Okay, the petal length and the petal width of all this data set. Yeah. So here we use that iris dot data, yeah, and then the square bracket column here represent the whole row, yeah, from 0 until 149 or until 150, comma, and then we only takes 2,3, the list here, 2,3, the with index 2,3 means that we take the second and third. But the second and third is we calculate from 0 here. Sepal length is 0, sepal width is 1, number 2 is petal length, number 3 is petal width. So this will be uploaded or downloaded, loaded into this X data. Then Y will be loaded with iris.target. Iris.target here is the last category in the data, yeah, the class label, which basically contains the species of the iris. So if we run this, yeah, here then print class label, comma, np.unique inside parenthesis y. This procedure, this method inside from the numpy will classify the unique class, yeah, will assign for each, will assign an integer class to the specific unique class within the iris dataset in the y. Yeah, in the Y, we have three, right? Iris versicolor, Iris setosa, Iris versicolor, and Iris virginica. So Iris setosa will be assigned with 0. Iris versicolor will be assigned with class 1. Iris virginica will be assigned as class 2. So similarly, later when you have classes, yeah, in biomedical engineering, let's say you have to assign this unique class identifier as integer. For example, you are trying to classify, uh, let's say, using microphone, the pattern of healthy people from people having normal cough or people having COVID-19 cough, for example, using microphone. Yeah, you have to do, of course, a little bit of signal processing, digital signal processing, and afterwards you have to assign an integer to which. After that, you put the data into row and columns table, yeah, like the iris dataset. Then you can use this np.unique to assign specific class. So, for example, for healthy people, you assign with 0, cough due to cold or due to influenza with 1, cough due to COVID-19, you assign with 2, for example. So this is some example, yeah, using just np.unique. So if there is no, if you don't use this unique method class np.unique, yeah, what we need to do is we need to write quite a long method ourselves in standard Python then classify whether that the data is never mentioned earlier or not. If it is never mentioned earlier, then we assign with new integer. If it has been mentioned, then we assign with the same integer as before, etc., etc. So this is the way that one of the advantage of using sklearn is that such a function is already standardized into its library. Similar with previously, the dataset, iris dataset is used frequently by machine learning society. So we just need to import dataset, and load underscore iris because it is used as a training for machine learning society. Okay, then
But
another feature. We go to the next slide. Yeah.
Pak,
So here, class label 012 refer to iris setosa 0, the iris versicolor 1, and iris virginica 2. Then uh, when we use machine learning, we classify into two different stages. The first one is the training stage, and the second one is test stage. In the training stage, we input known data with its known sample, with its known class, and we want the machine learning to be able to update its weight, the algorithm to update its weight factor. Yeah, remember weight factor. The weight factor is the number connecting the first layer of neuron to the second layer of neuron with certain algorithm, either Perceptron, Adaline, or later we'll use regression logarithmic, etc. Then after that, we want to test whether that machine learning, the weight that is being already resulted from the train, can really classify real data. Of course, the real data is something also that we have known for sure that this data belongs to iris setosa. This data belong to iris versicolor. This data belong to iris virginica. So to do that, then since we have limited data, 150 total sample, we will separate the data for training and then for tests. Yeah, in this case we split 30 percent for tests and 70% for training. So from 150, 45 sample will be used to test the data after the algorithm find the correct weight. You can optimize the weight of the junction of the connection. Then 70% of the data, which is 105 sample from the 150 sample. Sorry, 105 sample from that 150 will be used to train, and afterwards the 45 sample will be used to test whether the obtained weight uh, can be used to test, can classify real data sample, known data sample, let's say like that, for calibration, for validation. So in sklearn, such splitting function is also already standardized. From sklearn.model selection, you just need to import that train underscore test underscore split, x underscore train, comma x underscore test, comma y underscore train, comma y underscore test. So we separate into four different variable. Train underscore test underscore split. This is the standard method from sklearn. And when we input the data itself, the x here, which contain 150 data, and the y is the class. Test size equals to 0.3, so it means we will take 30% as from the data as test data to test the data after it is being trained. Then the random state equals to 1 is to specify the random variable. Then stratify equals to y. The random state 1 means that the random is true, so the data will be shuffled. It will not, so it is arranged into 30% test and 70% training, but the order how the data is being shown is not as the previous order of the data, but they are being shuffled. In this case, then the training. So it's not like from 50 data that we have collected. Let's say for iris setosa, 35, the first 35 for training, the last 15 for test. No, not necessarily like that, but can be one, for example, first for training, then first until 3 for training, 4, 5 for test, and then 6 until 7 training, then 8 until 10 test, something like that can be shuffled. Yeah, this is how it works when we specify random state equals to 1. Then using stratify equals y, we make sure that the class proportion is maintained in the same in the training and test data. So yeah, the stratify method makes sure that the class proportion is maintained the same in the training and test data set. It means if we have 3 classes, in the percentage will be maintained the same. So in this case, we happen to have the same 50, 50, 50, 50 setosa, 50 versicolor, and 50 virginica. So for training, yeah, 35 will be taken from each of the class, 35 from virginica, 35 from setosa, 35 from versicolor will be assigned for training, and 15 for each class will be used for the test data set. Okay, so if we run this this cell, yeah, from Scikit-learn model selection import train dataset. Okay, so it's already now being split into training data and test data in this variable x train, x test, y train, y test. So now using the next cell, we want to print how many are there, yeah, using this method in NPy and NPy. How many are there in the Y? How many are there in the Y train in the class? Yeah, this one. How many classes is assigned for the training? How many classes is assigned for testing? We run this cell, then we obtain label counts in Y equals to 50, 50, 50. So 50 from setosa, 50 from versicolor, 50 from virginica. In the Y train class, 35 from setosa, 35 from versicolor, 35 from virginica. And for testing, 15 from versicolor, 15 from setosa, 15 from virginica, etc. Okay. Then yeah, this is when checking whether the label proportion in each training and data set can be, the checking can be done using the numpy's bin count function. Then afterwards, we use standard scaler. Remember in the previous chapter, after one of the last discussion was we would like, in order to speed up learning position, yeah, in order to speed up learning position, we would like the class to be located in surrounding the average of that class population. So in that case, then, so instead of having random number, not random number, but that number of the petal length, for example, we will put the mean as 0, and then the surrounding part as a fraction between 0 and 1. So this we have to do it manually when we use the standard Python, but using Scikit-learn, we can use a standard function called as standard scaler. Okay. Okay, so we have split the data labels in the first hour, right, into training and test data set. Yeah, into training and test data set. Then so each of the class, the data that belongs to certain class is separated into 70% training in this case, yeah, and 30% for tests. Okay, and after that we use when standardization. Standardization means that we do several pre-processing before we use the data. We put the data into the machine learning algorithm, in this case in Perceptron algorithm. Okay, then in In Scikit-learn, that method is simple, yeah. So we don't really need to write our own code, but instead we can use this standard scalar class. Okay, standard scalar class. Let us use this in the notebook chapter 3. So this one is standardizing the feature. Yeah, from sklearn preprocessing. Yeah, import standard scalar method. Yeah, sc becomes the standard scalar function. Yeah, then sc.fit. The parameter is xtrain. So xtrain is all the data sets that have been grouped for training purpose. So then this xtrain is being standardized, is transformed using sc dot transform using xtrain, sc dot transform xtrain, and then transform into xtrain underscore std from abbreviation from standardized. Similarly, we do also standardization with the X test. Yeah, the X test, all the data sets that have been grouped, which is 30% from the whole data set that have been grouped for test purpose, is being standardized in surrounding its average mean. So from here, we run here. And yeah, so now it is already standardized according to their uh, mean and or average and standard deviation. Okay, then we start with the training of the perceptron. Training of the perceptron is also can be done quite simple using sklearn. Yeah, so here, uh, so we do multi-class classification. So in previous chapter, we have used perceptron, but only we do binary classification between two different classes. But using scikit-learn, we can use perceptron for multi-class classification using one versus res or OVR method, yeah, one versus res method that will fit the three flower classes, Setosa, versicolor, and virginica to the perceptron all at once. So here from sklearn dot linear underscore model, import the perceptron algorithm. Then the ppn data is the algorithm, the fitting variable, yeah, from perceptron with maximum iteration of 40. Yeah. Eta, remember, eta is the learning rate, is set to 0.1 here, and we make it random. So the learning stage or learning steps is made random, not according to the order that has been set from the data itself, but we shuffle the learning process. Then we use ppn.fit method, yeah, to fit the uh, training the data features xtrain, which is already standardized with the class that is assigned to it. Yeah, the class here versicolor, setosa, and virginica. In old version of Scikit, yeah, the max iter usually is called as n underscore iter. So be careful if when you run it doesn't run properly, then maybe you have newer version. In newer version, then an iter is changed to max iter. Okay, so let's try to learn this. Yeah, this already we have standardized the data to surround its mean with the diameter of the standard deviation. And then now we run the fitting algorithm or the machine learning algorithm. Yeah, ppn equals perceptron and ppn.fit, fitting the xtrain, the standardized data into the class, the wide range. So the perceptron here, yeah, run. This is the result. Perceptron alpha equals to n 001, class with none, early stopping false, eta is 0.0, eta is 0.1 here. Fit underscore intercept true, maximum iteration is 40. And then number of iteration, if no change, is 5, etc., etc. Then After that, then we can make prediction. So it is now already fit. Yeah, the using testing, using training, it's already been trained using the fit method, and then we test with try the obtain perceptron, yeah, which is we already obtained here in this output. Yeah, it is already mentioned. The alpha is 0.0001, etc., etc., and the data is being shuffled, etc. Yeah. Then we try to use it to predict the test data set. The test data set is 30% from the whole data. Yeah, using this one, making prediction using predict method. Y underscore pred equals to ppn dot predict from the X test STD. So in previous slide, we use X train STD for the training data set, which is already standardized or scaled. Then for testing whether our machine learning perceptron works or not, we use the X underscore test underscore STD, the standardized test data set. Then from here, we can print the misclassified sample. How many sample is misclassified into class which it doesn't really belong to. Okay, so here is %d here for integer. Yeah, this is to represent the variable as integer. Percent inside the parenthesis y test y underscore test. This is shown if the test sample is not equal to the predicted predicted data. So the y test here is the class from the test sample that we have already known, that we have classified from the raw data set which we have, yeah, the iris data set. The y underscore pred here is the predicted data set based on the perceptron that we have just trained. Then dot sum means that this is the sum of the misclassification. Okay, so for example, let's see, misclassification accuracy equals to accuracy equals to -1 minus error. So how many errors is there? Let's try. After we obtain this perceptron, yeah, then we run this one. Y prediction equals to ppn, the perceptron. ppn is from the perceptron class or perceptron of structure dot predict x text standard. We run. Okay, so the misclassified sample is only one. Okay, the misclassified sample is only one. From there, then we can show the performance metrics of this learning, this machine learning, yeah, using the metrics module. Yeah, what are the metrics module? So from Scikit-learn dot metrics, we can import the accuracy underscore score. Yeah, this is one method to show the accuracy of our machine learning after we have trained it. So the accuracy percent dot to f, so means this is a floating number with 2 digits behind the comma, behind the point. Percent accuracy underscore score. Then inside the parenthesis y underscore test, comma y underscore pred. Alternatively, using score method that combines predict with accuracy score. Yeah, so this is accuracy underscore score is imported from accuracy underscore score at the Scikit-learn dot metrics. We can also use ppn, the predict combination of prediction, yeah, in the perceptron itself with method score from with the parameter of x test std with comma y test. So this means it is predicting at the same time immediately showing the accuracy score. While the previous one, we first using predict, yeah, here calculating the predicted y output, and then after that use the method accuracy score to see if how accurate is the prediction. So in percentage, yeah, 1 minus error in percentage. So for example here, if using the first method, by importing the accuracy score method from Scikit-learn metric, we obtain accuracy is 0.98 or 98%. Second way is by immediately print the accuracy while predicting the y from the X test standard. Yeah. X standard predicting the y pred, then immediately, although it is not mentioned here, and immediately comparing it with the class from the original data. Yeah. So similarly, we obtain 0.98 accuracy or 98%. Okay. Then we try to plot, the decision region. Yeah, plotting the decision region. We here x underscore combine std. This is combining all the, now we combine again the train data and the test standard, the test data, the standardized training data and standardized test data. The y is also combined between the y or the class for training and the class for testing. Using this, this is NP v stack. The NP h stack is the horizontal stack. The v stack is the vertical stack. Then the plot decision region here, the x will be the x value, which is from the combined from this combined value of the training and the test data. The y is the combined value of the class. The classifier is Perceptron here. And then the range of the test is from 105 to 150. So this is from the 150 data, the train is the 35 data, the 45 data available. So the x label is written as petal length, the y label is petal width, and then the legend is, this legend is put in the upper left. Then we plot the figure, showing this decision region, based on the coordinate of the combined standard, and then classifying it as the three different classes, 0, 1, and 2. So this is the result. Let's try in the code, in the notebook code. Okay, so from here, from matplotlib colors, import listed color map, import matplotlib.pyplot SPLT, and then we define the plot decision region is this one. So this is already from the book, by Mr. Raschka, and then we define which one is the minimum value of x, the maximum value of x, and minimum value of x2 and maximum value of x2. Then using this, so we just use this as it is, without further modification, and then so we can run this so that it is defined, the matplot, the plot decision region. Okay, after that, then we plot the Perceptron model here. Okay, there's an error here that plot decision regions is not defined. Okay. So let's see, it's supposed to be defined here. Okay, from here, no error message. If you try it also in your notebook, if you can follow these explanations while trying in your computer also, using. No, good. Maybe have to rerun it. User locally Python launcher. Okay. Use an explicit list instead. Okay. I don't really understand yet. So, but anyway, we are successful to plot the three different classes after being successfully classified by our Perceptron algorithm into 3 different classes. So 0 is Iris setosa, yeah. The 1 is the blue is Iris versicolor, and the green one is Iris virginica. So we see here, as we have shown earlier, using printing, using by print method, we have one misclassified data. Here you see green one, and the accuracy is 98%. Actually, more accuracy, if you see here, I'm not sure. There are more of this virginica, which is classified as iris versicolor. Somehow it only shows this one. It only recognize this one as iris virginica, which is being put into the iris versicolor region. Okay, so that is how Perceptron is being implemented using Scikit-learn. So as we can see, a lot of work which in the previous chapter we have to do manually can now be done more automatically and more user-friendly for us, yeah, which is not maybe a specialist in machine learning programming. Okay. So, yeah, the perceptron algorithm, as you have learned in the previous chapter, specify immediately with the binary classification method. Yeah. So if the weight, the z, which is the multiplication net multiplication input of within the weight and the x, is above certain value, it classifies as 1. Below that, it's classified as 0 or as minus 1. So because of this, the perceptron algorithm can never converge on data set that aren't really perfectly linearly separable. As actually our 3 data set, yeah, versicolor, setosa, and virginica, they are not that linearly separable. So that is why in practice, the use of perceptron is not really recommended. However, we often use it for learning purposes, yeah, because it is the, let's say, the easiest machine learning algorithm. And so for this chapter, we start to learn logistic regression as for binary and linear classification problem. It is also very easy to implement and can perform very well on linearly separable classes. And it is one of the most widely used algorithms for classification in industry. For binary classification, it can be used for binary classification, so in separating 2 classes, but it can also be extended to multi-class classification using, for example, one versus rest technique, yeah, similar like the perceptron before. Now the difference, what is the difference? This is based on the odds ratio probability, yeah, the probability ratio in favor of a particular event. So P here, probability of the positive event. So this is if we, let's say we classify 2 different classes. So probability of the positive event divided, or the ratio of probability of that positive event compared to the other non-positive event. Yeah. So the positive is by P divided by 1 minus P. Positive event here is the event that we want to predict. For example, probability that a patient has a certain disease. Okay, so P equal what? 0.85. And 1 minus P will be equal to 0.15. This is into 2 different classes. Then Y equal 1 here means class. Yeah, the class will be classified as 1, for example. From there, from this probabilistic, yeah, logistic regression, probability ratio, then we can define logit function. The natural logarithm, yeah, actually ln, yeah, in normal mathematical symbol, but we write it here as log it. Yeah. The natural logarithm of that odds ratio, of that probability ratio, the log of the odds. So the logarithmic, the natural logarithm of that previous function, yeah, p divided by 1 minus p. So the logit function's input value is between 0 to 1. Okay, so P is between 0 to 1. And that's probability, right? 0 means zero probability, means it will not happen at all. 1 means that it definitely will happen. So in the range of an event, of a positive event that we want to predict is usually between, not usually, should be between 0 to 1. So that is why it is the entire real number range. So the logit of P, for example, that Y equals to 1 for X data set, for a certain data set X, will be equals to, first, similar like before, this is the net input multiplied to the weight factor, W W0x0 plus W1x1 until WMXM. So this represents the features of that data set. Yeah, so M features, for example. In the case of iris data set, we have actually 4 features. Yeah, X1 until the X4 plus maybe some bias. So usually the X0 is allocated for bias, reserved for bias. But it depends. For example, in the previous example, we only use 2 features, petal length and petal width. Okay. Then this will be equals to sigma I from 0 until m, Wixi equals to W, the transform of the weight factor multiplied to the X factor. Yeah, the X factor here is the input data set. So the probability of Y equals 1 for X is the conditional probability that a particular sample here belongs to class 1, given its features X. So when we put a feature, when we particular sample, have this feature X, X0 until XM, we put into the algorithm, then it is multiplied by the weighting factor, WO until WM. Then P, the probability of it belongs to class 1 is represented by this function P y equal 1 when with this line, then when it is X. Now, what will be the function of that conditional probability? It could be many functions. And but one of the most common function is to use logistic sigmoid function, or for short sigmoid function. So we are interested in the inverse form of the logit function, predicting the probability that a certain sample belongs to a particular class. So the inverse form of logit is logistic sigmoid function or sigmoid function. The phi z, yeah, z here is that value W t, the transpose of the W multiplied to X equals to then W0xo plus W1x1 until WXM. Yeah, then this value, the net input of this value is then input into the logistic sigmoid function here as this Z. So 1 over 1 plus exponent minus Z. WO or W0 refers to the bias unit. This is usually an additional input value, not belongs to the actual input data set, but additional input value to give a bias. So W0 refers to the bias unit, additional input value that we provide X0, which is set to equal to 1. Okay. So for example, let's try to draw the sigmoid function first. So using matplotlib.pyplot, which is we import SPLT here. So then import numpy as the standard numerical procedure in Python. We import as np, and we define the sigmoid function z, which will return. This is from the formula of the function 1 over 1 plus exponent minus z, right? Or from np dot exponent minus z. Then, for example, let's start with z, arranging it from -7 to 7 with interval of 0.1. So it means -7 minus 6.9, minus 6.8 until 6.5, 6.6, 6.7, 6.8, 6.9, 7. Then phi z equals the sigmoid of z here. So this is also an array calculating with a value from this range. Okay. When we plot z, comma phi z, and plot the line here, x line as color k is I think black. Yeah. Plot the y limit, yeah, the y scale limit from minus 0.1 until 1.1. The x label is labeled as z. The y label is labeled as phi z here. Yeah. Then the ticks and the grid line of the scale. Yeah. The y-ticks is from 0 until 1 with an interval of 0.5. The ax, yeah, this is the grid, and the ay.y-axis dot grid through, so to show the grid. And then plt show. plt dot type layout and show. plt dot show. So let's try this in our logistic. Okay, here is trying to plot. We run. So this is the result. Yeah, function of, we try to plot the sigmoid how so that we have an intuition how it looks like. So from this is from minus 7 until 7. So at 0, 1 exponent 0 is 1. So 1 plus 1 is 2. So 1 over 2, which is half. Yeah? So with that 1 and in the denominator, basically it will add this add up the y-axis. Yeah. So instead of minus 0.5, for say if you don't have that 1, exponent 0 will be 1. So the value here at 0 will be 1. Yeah. Then at minus infinity, the value will be 0. Then this will be infinity. So this with this one, we limit the value between 0 and 1. Since we know that the probability always range from 0 to 1. Now the problem is how is the probability is being distributed along that 0.1. With the sigmoid logarithmic sigmoid function, we define it as like this, like a sigmoid asymptotic function. Okay, so then so this is how it looks like as we have successfully draw in using our code. Okay, now a little bit of review. If we compare this logarithmic or logistic regression with other line, how does it differ? So in other line, remember that the activation function is linear, yeah, from whose value is when the z, yeah, the z here. Let me annotate now. So this is basically z, right? This is the z function. Remember that the z equals to phi z, yeah, phi 0 dot x. Okay. Oh, sorry, not that one. Yeah, it's correct that the z equals to the transpose of the weight factor here dot the x. So this one will be equals then to w0 x0 until wm xn. So here when it is negative in the linear function in the other line, like this, when the value of the z, and this is the value of phi z, yeah, the y-axis is phi z, in the other line, then if it is negative, it will also be given negative value. If it is positive, it is given positive value. With no limit, yeah, no limit of the value of the x of the function value. However, and then after it is being trained, then we put into the threshold function, similar like the perceptron. In sigmoid, on the other hand, this value it becomes so from the z, the value we limit from If it is 0, it should be half. Yeah. And then if it is minus infinity, then it will be 0. Okay, so this one, this equals to 1. 1, this is 0. Okay, so this is the difference between Adaline and sigmoid function. Yeah, in Adaline, then it is linear, but in sigmoid, it looks like a sigmoid function, and there is a limit of the probability between the value is between 0 and 1. In linear, no limit. Okay, in linear Adaline. Okay, so yes, moment here. So from the definition of the cost function, yeah, cost function yz is equal to the returning the np.log sigmoid of z. This is the cost function. For zero, it's returning when 1 minus sigmoid z. So this is the cost function value. Yeah, the cost function value means the error. Yeah, the error which we need to minimize. Okay, which we need to minimize. Then it will we range from the z value from minus 10 until 10 with an interval of 0.1. So phi z equals the sigmoid of this z. And then the C1 calculating the cost one here, yeah, the sigmoid value, the logarithmic of the sigmoid. And then remember the logit function in the C1, then label this as a JW if y equal 1. Then for y equals 0 for the other class, yeah, because this is binary classification, we put into the cos underscore 0, yeah, which is represented as log of 1 minus sigmoid z. And we plot while the limit in the y-axis is from 0 to 1, 0, yes, and then 5 so for to 5.1, then x limit is from 0 to 1. Okay, so let's try in our notebook how it would look like. Okay, first is running the definition of the cost function. Yeah, take some time. A little bit longer. Yeah, let's wait a little bit. Runtime discontinued. Yeah, what happened? Okay, let's try again. You can try also in your Google Colab. Yeah, if you have found it, the result, please let me know. Maybe you can share your screen then. Because I'm not sure why it takes long now in my Google Colab. Yeah. Have you successful any of you been successful to run this cell, learning the weights of the logistic cost function? It's still running and takes quite a long time. Usually it is quite fast. Automatic document saving is pending reloading may fix the problem. Save and reload the page. Okay, let me save and reload the page. Any of you have tried also this one? The cells is below this
Logistic cost function ya Pak. I
learning
have
the weights.
tried.
Yes,
I
have you
have
tried?
tried, but with your code. I haven't transferred it to my code, but it's successful.
Successful. Is
Using
it
your
successful?
code. Yes, but using your code.
Yeah, basically, I'm using also the code from the book actually, so not.
Oh yeah.
Can you share your result? Your, screen share your result, please.
But you disable participant to share.
Okay, okay, wait a moment. Yeah, yes, this should be okay now. Okay, so yeah, this is supposed to be the result, yeah? Correct. This is one. This is after you have run it. Try to run again, please. Okay, it works, yeah? It works well. So it plots the logistic function, sorry, the cost function. You remember JW, yeah? JW is the Jacobian error, yeah? The error function that has to be minimized, the error that has to be minimized. So similarly like this, so the blue one shows that the GW if y equals 1. So it immediately will be minimized, yeah, into 0. Well, if the y is 0, then the error function will just increases. Okay, so can I share my screen now? Okay. Yeah. Somehow it's still error. I don't know. Maybe with my Google Colab, I will check later. I will reload later, maybe if necessary. Anyway, let's just continue the theory part for a while. Or it's in my internet, which is in problem. But if the internet in problem, why?
I think you should run the previous the previous class.
Previous line.
Yes.
Okay, so okay, apparently no, not the problem is in the Google, yeah, in the Google somehow Google slide. The Google slide also cannot be run here. Okay. Oh, you mean here? Yeah, this one has to be run as well. Image file name, because before that there is only here, which I think also not. Yeah, I have problem with my Google. Yeah, but I don't think I have problem with internet, because if I have problem with internet, the Zoom will also be disconnected. Yeah, so okay, let's just pause the recording for a while. Logistic regression, then logistic regression using gradient descent. Yeah, so GD means gradient descent. So similar like the gradient descent algorithm we have learned for other line in the previous chapter. So here the eta is defined as the learning rate, and underscore iter is defined as the passes over the training data set. Random underscore state is the random number generator set for the random weight initialization. Then attributes here, W underscore is the one-dimensional array. This is the weights after the fitting. Cost underscore is the list. Sum square cost function value in each epoch. Then we define the initialization methods, yeah, with taking the function of the eta, the learning rate, and the maximum number of the iteration, and whether we shuffled it or not in the random state. So or everything is assigned to the self method. Then we define the fit method, yeah, from x and y. This is the training data. X and y is the class, yeah, from the training data set. Then parameters, x is the array like the shape, the training vectors, the y is the target values. And so this function will return the self object. Then what else? Rgen equals to the random, so this is random. So for I in the range of for when the repetition is still within the maximum iteration that we allow, which is defined in this n underscore ita. So here it means we allow it to repeat the repetition, to repeat the learning, yeah, until maximum 100 times. Then it will calculate first the errors. Yeah, this is the weight function. Then computing the logistic costs now, yeah, using minus y dot np dot log output minus 1 minus y dot np dot log minus 1 minus output. Then this becomes the error or the cost function, the jw. Then defining the net input. This is basically the x, the weight multiplied by the x. Yeah, this is. Then the activation is the logistic sigmoid function. Yeah, 1 over 1 plus exponent of minus z. The z here is from the term will be taken from this net input. Then after that, predicting uh, the data, yeah, predicting the y using the x value. So where self-activation is larger than 0.5, then it will be assigned as 1. So in the probabilistic function, when the value is larger than 0.5, the probabilistic result is larger than 0.5, then class 1 will be assigned. So when it is less than 0.5, it will be assigned as 0. Yes, so this is binary classification similar to Perceptron. So for example, here when we want to separate between iris setosa and iris versicolor, yeah. Setosa we assign as class 0 and versicolor we assign as class 1. So x underscore train 01 subset. So we put the data set here into x train, yeah, and y train, the class. Then using logistic regression with gradient descent with 0.05 of the learning rate and maximum iteration of 1000 and shuffled between the data set is being shuffled. We put into the fit logistic regression gradient descent fit function x train 01 subset and y train 01 subset. Then plot the decision region and then classify it. And this is the result. This is the iris setosa, the 01, the red one, and iris versicolor, the blue one. Yeah. Unfortunately, now we cannot try in the notebook. Please try on your own in your system. Because now apparently I have some problem with my system. Okay, so I think that's all for today. We will continue again next week, inshallah, hopefully, with this logistic regression function as well as with other algorithm using the Scikit-learn module.